Now what we will do is to take this idea and let us look at certain timing diagrams, okay, so that we understand what we can, how the data flows through the system and what is going to happen there, okay. So initially we are going to draw this as if there is no flip-flop over timing overhead, that is the delay added because of the flip-flop in terms of setup, hold and clock to queue delay is 0, okay. We'll just start with that so that we just focus on what happens to the data flow in a pipeline system like this, okay. So I am going to look at this clock, some combinational block C1, another combinational block C2, and then I have a okay. So right, so this is D1, Q1, D2, Q2, D3 and Q3, okay. So we have to wait for the data that comes into D1 to arrive at Q3, okay. That is what we are going to define as latency, right. And the throughput is of course when we can feed the next this thing, right. So if you look at this guy, I'm talking of the clock here. I'll draw the clock slightly realistically. It will be like this. Okay, remember all these are multi-bit data, okay. It could be any number of bits. That means if this is 8 bits, it means there are 8 flops and 8 inputs are coming in from outside, right. So all of this I am going to only treat as multi-bit data. I am not assuming that any of this is 1 bit of information, okay. So now I am going to, obviously when I say it's a D flip-flop, I mean it's a positive edge triggered D flip-flop, okay. So what we'll do is maybe we'll consider even the delay of these flops straight away. I think that is sort of makes it easy. So this is my sampling edge, by the way, okay. This is my sampling edge, and remember that around this sampling edge there is a window which is called the setup and hold window, around which data should not change if I want it to go through correctly. So I am just marking that zone around the clock edge where my data should not change, okay. So please follow this principle very diligently of marking these regions, the sampling edge and all that stuff very clearly, okay. So now in order for data D1 to be captured, okay, I am going to call this as FF1, FF2, FF3, okay. Flip-flop 1 has to capture the change in D1 and send it into Q1, right. For that to happen, obviously my D1 should change before this setup and hold time window. Okay, so this one is some data state 0, this is 1, okay. So it's going from some 8 bits to another set of new value for the 8 bits. I don't care what they are, they're basically the values corresponding to that. So for simplicity, let me assume all these numbers are 8 bits, okay. Just for a concrete example, it could be, each of them could be different numbers, by the way, okay, I don't care, but I am just saying, for example, this 8 bits Q1 going into the combinational block could eventually become 4 bits and D2 might only be 4 bits, right? That also is possible, but for now I am just assuming everything is 8 bits, okay. So now D1 has changed from state 0 to state 1 and the flip-flop needs to capture this data and it will be made available at Q1, okay. So if I look at my Q1, I do not know what the data was before this because it is in an unknown state. I have no idea what was captured, right? And then at the clock edge, it is going to take at least the clock to Q delay for the data to appear at the output on Q1, okay. So if you look at this, you will have some transitions like this and then it will stabilize to Q1. So again this one I will I don't know, I am going to call it 1 like this, okay. Now this delay from the clock edge to this is called TCQ, okay. I am calling it clock to Q delay, right? And after that Q1 will simply remain at the same state until the next clock edge, okay. So this is, if you look at this, this is clock edge 1, 2, 3, 4 and so on, right. So event 1 on D1 has been captured on clock edge 1 and has been sent into the system at Q1, okay. Now Q1 is an input to some combinational block, okay, and we know that the combinational block will start reacting to these changes immediately. So if you look at the output D2 of this combinational block, okay, it is going to appear like this. It will start, making some changes and then it will settle to its final value, okay. It can, okay, so I am going to represent this also by 1, but remember that D2 and Q1 need not be the same values, okay. D1 could be one 8-bit number. The combinational block C1 is processing that and resulting in another 8-bit number on D2. But I am just saying it is corresponding to that event 1 that came into D1. Okay, this is the same convention I have been following all through in this course, right. So I do this, right, and then it appears at D2, right. Now what happens? The next clock edge is arriving after a certain time, right, and therefore if you look at my Q2, right, obviously D2 must, all the changes must have settled before that setup window of the second clock edge, okay. Remember that this one is the setup and this one is the hold, okay. So D2 must also change, all the changes must have settled, okay, before the setup time of the second clock edge, right. And once that is done, you will see that Q2 just like Q1 will be available after some changes like this after the TCQ. So if you look at this again, TCQ, right. Now, so this again is event 1, okay. Okay, so I will take this off because I don't have space here. Okay, I will mark this later again. This is just to keep in mind that that's the setup and hold time there. Okay. So now the question is, Q2 is processing like that. Q2 will then, come out after some time, right? Now you can ask the question, can I feed event 2 into this system at the second clock edge? Well, it turns out yes, because the second flip-flop is actually holding the data for the combinational block C2 to process. Okay, so if I look at this, the second change, the event 2 can happen here. Again, it should happen before that setup window. Okay, and this is event 2, right? Now, event 2 has changed, right? And D1 has therefore changed to event 2. At that clock edge, again, you will have all these changes and then it will come out here at Q2. This is 2. This is event 2. Okay. Now, Q1 again is an input to C1, which is a combinational block, and therefore the moment Q1 starts changing, your D2 will also start changing, which is the output, right? And it should settle before the second clock edge. So this is event 2 again, right? And like that the data is going to flow out, right? So let us just complete this. Q2 event 1 is available here. That is, so if I plot D3, right? So basically, essentially D3, that's the output of a combinational block again. So it will start changing. This is event 1 on D3, right? And obviously at the clock edge Q3, okay, the data will be captured by the clock edge. And after some TCQ, this event 1 will appear at the output here. Okay. Now, what is going to happen therefore is that event 1 that came into the system at the first clock edge will appear at the output only after the third clock edge, right? Depending on the number of stages of pipelining that you have. Okay. Now, likewise, in the next clock edge, subsequent clock edge, you will have event 2 coming out. So if I just continue this diagram here, right, and just plot what's going to happen, you will have this clock edge like this, and you will have event 2 coming here. So event 2 is going to propagate all the way like this. Okay, this is event 2 and D3. Obviously, because Q2 and D3 are input and output of the combinational block C2, you will start seeing changes here as soon as Q2 changes, and it has to settle before the clock edge. So this will be event 2. So what you see is event 1 is flowing through the pipeline in a particular way. Event 2 is following that after one clock cycle, event 3 after another clock cycle, event 4 after another clock cycle. So what you see right away is the flip-flop's job is to actually sequence these events in exactly the order that it came into the system, right? You cannot, it's not okay to miss one of these events, that means you have dropped a brick, right? And therefore you will end up ruining the whole system. Okay, and having understood these delays and these things quite well, right, we can also ask ourselves now, how fast can I operate this pipeline system, right? What is the minimum clock period, right? What is the clock period, by the way? If I just continue this, if I just extend this here, we are talking about this being the clock period, right? And I am going to now ask, what is the thing, okay, what is the minimum period that is allowable for this? So let me call this delay as some in what color, let me use dark green, TPD1, TPD2. Okay, so if I were to have this delay, what does TPD1 means? It's a propagation delay of that combinational block. That is, you take the worst case path delay, and after that you are guaranteed that all the outputs of combinational block C1 have settled. You are guaranteed that they have settled, right? So that is what you mean. So when you look at this whole thing, we are talking about TPD from the time Q1 settles to this thing. We are talking of TPD. And you also know that D2 must settle at most at the setup window, right? Therefore, I would say that this edge in red here, I will say this edge can move as much as the setup window there. If you move any further, you will lose the data because you have violated the setup time of the flop, and therefore you can assume that you can bring the clock period down to the extent that this propagation delay exactly is equal to the setup time. So therefore, what we will do is we will just say this has to be T setup. Okay. Now, based on this, I can write one equation for the clock period. TCLK should be greater than or equal to TCQ, okay, plus the TPD plus the T setup. Now, this must be true. So, remember, this is for TPD1, okay, but this must be true between any two flip-flops, right? Remember that if combinational block C2 had that old person in that brick queue who took 5 units of time, then you will have the whole thing will go for a toss, right? And therefore, T clock, when I write between these two flops, right, I will say T clock must be greater than, same thing, TCQ. Remember, these can be identical flops, so therefore you can assume that they have exactly the same delays, right? Plus TPD2, okay, plus T setup, right? Now come to the third, between this flop and the next one, the same thing has to hold between any two flops, and therefore I will say in general T clock should be greater than or equal to TCQ plus T setup plus max delay of all the combinational blocks between the flops, that is TPD1, TPD2 in this case. If you had a 3-stage pipeline, then you have to make sure that all of them is, this thing. And because we have this maximum constraint, so remember, this is what we had the case when we had 5 units and 9 units, right? The max between 5 and 9 is 9, and therefore that is what determines the the fastest at which you can operate this system, right? So essentially this is this, the intuition that we got from that brick also shows up here through this max constraint between these flops, right? So effectively what we have now done is we have simply been able to show you how data flows through this pipeline, right? Now I leave it to you as an exercise, saying in the unpipelined case, when we did not have, flip-flop 2, right? So let me also show you that. I will say please draw this as an activity question, okay? So this is the clock. I am combining the blocks C1 and C2. Clock. Okay, so this is D1, Q1, D2 and Q2. Only 2 flops, therefore there is only D2, Q2, and therefore I will call this output as Y, in between output as Y, right? So you could treat this as one combinational block, okay, whose delay is TPD1 plus TPD2, right? So if you consider this as one big block without pipelining, obviously you can write the same constraints here. T clock should be greater than TCQ plus TPD1 plus T setup, right? That's it. And therefore my T clock was going to be determined by, so the T clock is greater than, I will rewrite this slightly, TCQ plus T setup plus TP plus TPD2, right? So let's take some sample numbers here. If TCQ is, let's say, 5 units of time, okay, 5 units, setup time is, let's say, 3 units, and TPD1 and TPD2 are 40 and 35 respectively, right? Then it implies T clock should be greater than 5 plus 3, 8 plus maximum of 40 and 35. So it is 48 units of time. Whereas here we are talking of T clock should be greater than or equal to 5 plus 3, 8, that is the same, okay. But I also have TPD1 and plus TPD2. So it is 40 plus 35, which is 75 plus 8. So it is 83 units of time. Okay, so clearly we have been able to reduce the clock period significantly, almost by a factor of half, and double the throughput of the system, right? And of course, because they were not equal, the delays 40 and 35, we paid a slight price. We were not able to exactly have it, okay. Now what is hidden here is that, look, every time you add a flip-flop, there is a certain delay associated with going from the clock to Q, right, and the setup time. Data has to be ready before that setup time, right. Because of this, you have what is known as the sequential overhead. This is called the sequential overhead, and this is what actually prevents you from adding one flip-flop at every, adding one pedestal to every staircase there or every step, because there is a penalty even in delay. If you keep adding like this, you are not going to get the benefit of pipelining eventually, right? So what is important to note is, in the throughput equation, we don't see the effect of adding so many flops, Okay, if I actually choose to add a flop after every stage and break it into a 10-stage pipeline, this throughput equation will just say T clock should be greater than TCQ plus T setup plus max of 10 delays, and it might end up being faster. But the fact is that in order to get the latency, you will see that the data has to go through at least one TCQ, right, at each flop, and therefore every time I add a flop, I am increasing the latency by a TCQ delay. Okay, so you will see, for example, what is the latency in this system, and what is the latency in this system. So the latency here is from this clock edge when the data comes in to the time when Q3 has the output stabilized and ready. So if I look at this, I am talking of this as my latency. Talking of this as the latency. So every time I add a flop, I will end up adding these TCQ delays to my system, right? And therefore, this system here will end up having lesser latency than the previous system there, even though the throughput was almost double in that particular system, right? As a concluding note, there is also, we only spoke about the propagation delay through these combinational blocks, right? But there could also be very short paths, okay, where, for example, if you take your combinational block, which is, let's say it looks like this. Okay, I have one output which is just going through an inverter like this, and an other output which is going through bunch of gates like this, some huge number of gates. So if the input D changes here, right, or A changes here, Y1 and Y2 are things, this may take 100 units of time to actually change and stabilize. That is what we call the TPD, propagation delay, right? This is the critical path for this circuit, quite obviously, whereas this could take only 10 units of time. Okay, and if that takes only 10 units of time, it could cause what is known as the hold time violation, right? So I will not get into that. You must just keep in mind that this very quick contamination of data can corrupt your system if it is not designed properly, and therefore you must also be careful about hold time violations in the system. But that is beyond the scope of this course, right? Just keep this in mind, keep this term in mind, hold time violations, and you will study about this in a future course. Okay, thank you.